Thanks so much for joining us tonight. We will be getting started in just a minute. Hello, everyone. A warm hello and aloha to each of you. Thank you so much for joining us tonight for Ask Me, our educational webinar series. My name's Audra Hines, Vice President of Care Services for the Golden West chapter of the ALS Association. I want to thank our lead sponsor for the Ask Me series, Mitsubishi Tanabe Pharma America, as well as our industry partner sponsors, Cytokinetics and CNS. Additionally, a huge special thanks to Cheryl Barber and Judy Stewart for their tremendous support of the California ALS Research Summit, and to all of our mission benefactor families. Thank you, thank you. It goes without saying, but I'll say it anyway. Your contributions are amazing. We could not make programs like this one tonight possible without these generous donations to the Golden West chapter. The mission of the chapter is to discover treatments and cures for ALS and to serve, advocate for, and empower people affected by ALS to live their lives to the fullest. On the services front, more than 15 care managers work tirelessly every day to ensure that our clients and families living with this disease have access to loans of critically needed medical equipment, referrals to some of the top ALS clinics and specialists in the country, navigation of insurance benefits, and emotional support through a variety of ways for the entire family impacted by the disease. It's this direct work that fuels our efforts in best serving our communities. On the advocacy front, we work on both state and federal levels as we grow our number of activists who want to help change the landscape of access to new therapies and better specialty care to impact real progress in the world of ALS. On the research front, we partner with clinicians and researchers who specialize in ALS so that we can provide programs to you like this one tonight and support the advancement of critical ALS research. To learn more about the Golden West chapter and the multitude of services we provide, please visit alsagoldenwest.org for more information. We're so excited to bring you this important annual educational program for the ALS community as a follow-up to the 13th annual California ALS Research Summit. The Golden West chapter is proud to serve as the founding sponsor of the Research Summit since its inception, and we're so grateful to collaborate with some of the country's leading ALS scientists and clinicians like the ones we have here tonight. Presenting the latest and greatest updates in the field of ALS research will be the chair of the California ALS Research Network, Dr. Clive Svensson from Cedars-Sinai Regenerative Medicine Institute. We're also joined by Dr. Catherine Lomenherth, Clinic Director of the ALS Treatment and Research Center at UC San Francisco, who served as the summit's co-hosts this year. They are here representing the members of the California ALS Research Network, who the Golden West chapter honored with our 2023 SE Commitment to Cures Award. They will update us on the outcomes of this year's ALS Research Summit, including a special presentation about the Barber ALS Research Awards. In addition, Dr. Lomenherth will share her presentation from the summit that's focused on the challenges and opportunities of increasing diversity, equity, and inclusion in both ALS research and clinical care. And we'll conclude our evening with Dr. Svensson's summary of the stem cell cortical trial for ALS, and we'll move to answering all of your questions in an open Q&A format with our speakers. So I want to invite Dr. Svensson to turn on his camera and sound. We would love to start with you. Thanks a million, as always, for being here. I'm going to turn it over to you. We're super excited for your insights from the summit.
Well, thanks so much, Audra. It's fantastic to be here. Sorry, we're still stuck in these Zoom boxes. I'm sure we will escape from them very soon to see everybody in person. So I'm going to talk about, first of all, the network. This Californian ALS Research Network was formed in 2010. It's an ad hoc group of ALS researchers, investigators, clinicians, and advocates. And we also have people from industry, government, and other partner organizations. And we all really volunteer our time and expertise to advance the network's mission. Current members are some of the founders of the annual California ALS Research Summit, I'm going to talk about in a moment. And we also formed the planning committee for this year's summit. And the vision of this network is to actually look at effective treatments and find effective treatments and cures, facilitate development and implementation of the best possible ALS research program in California, and put California at the forefront of ALS research worldwide. And that's quite a tall order. I think we've been going now for 13 years, is our 13th summit. And I think over these 13 years, we've really done a lot in the state of California to increase awareness about research, education, and other aspects of ALS care in the community in this wonderful state of ours. So let's talk about the summit in the next slide. So this is the summit. This is, again, the 13th time we've done this. Every year we hold it. It's really, again, to bring everybody together in the same room. And we have an amazing group of researchers throughout the state of California. We have some amazing institutions. We have, for instance, from the north at Stanford, all the way down to the south at UCSD, and everything in between, all the amazing institutions we have, get together to discuss the latest advances in ALS over the last year. This year was in person. The last 2 years have been Zoom, so we did all get together. We had over 200 registered attendees. And again, the unique aspect of this meeting is it doesn't just do kind of basic science, and it doesn't just do clinical. It doesn't just look at new drugs and industry. It combines all those three together, and we all sit in the same room and discuss how those three are interacting in order to push forward research and clinical care for you guys, for the patients that have ALS, especially in the state of California. We had 40 guest speakers. We had a lot of panel discussions and presentations. And we also had participants, from outside the US and from outside the US, even as far away as Japan, to discuss some key elements of our program. Now, the next slide. So what did we find this year? And I'm just going to very briefly give you a high-level view. We were locked in this room, 200 of us, for 2 full days. And we started with some very interesting discussions about how we go forward with drug trials. And this was an interesting discussion led by John Ravitz, who discussed the pros and cons of moving to drug approval before perhaps completing a lot of big trials, what we call a phase 3 trial. As many of you know, for a drug to get through to the clinic, normally it's got to go through a very large phase 3 trial, which means hundreds of patients and lots of money, a very expensive process. And so one question is, maybe you could do a smaller phase 2 trial to get that drug approved. And I think we had a very lively discussion. On one hand, you might think this is going to be a good thing because more drugs get onto the market. The danger, the downside is if that drug really didn't work and you need a bigger trial to prove it, you might have a drug on the market that could be very expensive that you have to pay for that really doesn't work that well in ALS. So those are the two sides of the story. We had a good discussion. And I think the end of that was if your phase 2 smaller trial is very strong data supports that it's having an effect in ALS, it should be allowed to go through to market, providing everybody agrees that level of effect is high enough. Very, very interesting discussion. We then went into some very complex biology. This TDP43 is a protein that you find in ALS brain. Every ALS patient accumulates this protein. We're trying to understand more about why, what it does. It's kind of like amyloid for Alzheimer's. This TDP increases in the brain. And you get different changes that occur, and we think that might be very important. And if we can block this effect of TDP43, it gets kind of like glue inside the brain cells, in the nerve cells. Maybe we can have some sort of therapy for ALS. We had a lot of discussion about that. And I think that's really built into industry because we're now discovering, and we heard a lot about this, links to the next 2 sections, industry is telling us that we're getting new ways to develop drugs for ALS. And I think one of the most exciting areas is in those types of ALS where we know the cause. And there's only a few types that caused by specific genes, as I'm sure many of you know. And one of them is SOD1. That's particularly rare, but if you have an SOD1 mutation, you will get ALS. And a company called Biogen presented some very interesting data showing that they can use a gene approach to knock down that bad gene that is being made in ALS patients, the SOD1 gene mutation, can knock down that gene effect. And it seems like a New England Journal of Medicine paper published recently that does seem to be having some impact on the disease progression. So look out for the continuation of that program. They're actually going to the FDA to ask for approval for this product. It's antisense oligonucleotide developed by Ionis Biogen together. And so if you have an SOD1 mutation, that is a very interesting thing to keep an eye on. And I think the same could be said if you have a C9 mutation or any other particular genetic form of ALS. It's worth keeping your eye on these new trials coming through. And there's a few more for C9, not as far along as SOD1, but I think SOD1 will probably lead the way. Much more on that coming over the next few months. So keep your eye on SOD1 and clinical trial and Biogen. We then move to my favorite area, which is we've been working on for a long time, is using stem cells to both treat and model ALS. And I'm going to go short here because I'm going to talk about that in the last part of this meeting this evening. I will also say that there's a lot of very exciting work using stem cells to model ALS. And in fact, some researchers now, we invited some researchers working on a technology called organoids. Now, believe it or not, we can make a stem cell from an ALS patient, very primitive type of stem cell, that we can then push to be neurons that die in the disease, motor neurons. Now we're building little clumps of neurons called organoids. So they're like mini brain bits. And what we're doing is actually putting a cortical organoid, the brain, and attaching it to a spinal cord organoid. We can make a little muscle organoid, and we can actually rebuild the circuit that undergoes degeneration in ALS. And we organized a pre-meeting with ALS Finding a Cure before the summit to really dig into these new models of ALS using organoids and stem cell technology. And I think you're going to keep an eye on that. Those models are going to be very powerful and will complement our mouse models significantly over the next few years. We then went into at-home care, genetic testing, and DEI, and you'll hear in a moment from Dr. Lohmann-Herth about this fascinating area of both looking at testing for ALS, and I think I'd encourage patients to talk to your genetic counselor, but think about getting genetic testing for the reasons I mentioned earlier, these new trials coming along for specific types of ALS. We heard from Matt Harms from Columbia, who's doing some very exciting work, understanding more about the genetics. And of course, diversity, equity, and inclusion is a very important aspect of the Golden West chapter. And we're going to hear a lot about that in a moment from Dr. Lohmann-Herth, about how important that is to think about that when we design clinical trials and encourage the whole community in California to be involved and not just some segments of it. We then discussed the sigma receptor and ALS, which is a specific pathway Richard Smith has been very interested in, and this is related to a drug that some of you may take called Nodexta, which really helps with some symptoms of ALS, particularly emotional symptoms that patients would have. So look at Nodexta and the sigma receptor, and we're trying to understand how that works. We then went on to look at early and progressive methods to detect ALS early. The earlier we can detect it, the sooner we can get you into a drug treatment. And even the testing drugs we found, and with Amylyx and others, and other aspects, we heard from a lot of industry and clinical folks that the earlier we get into a clinical trial, the more chance the drug has of working. Which sort of makes sense. If you go in when the disease is too progressed, then the drug can have a better effect. So we're trying to understand how to detect ALS earlier. We had a lot of discussion about new ways to do that. Finally, the poster presentations, and that was very exciting in the annual Barber ALS Research Award. And I'm going to ask Dr. Lohmann-Herth to put a camera on, and you've heard enough of me for now, and I will turn my camera off and let Dr. Lohmann-Herth tell you about the award.
Thank you so much, Clive, and welcome everyone. It's such a privilege for me to introduce Jim Barber to you all. He is someone that I know well as a as I had the privilege of being his doctor. So Jim served in Vietnam. He graduated from UC Santa Barbara as well as UC Hastings College of Law, and was a very successful attorney for more than 30 years before he was diagnosed with ALS in 2006. During his nearly decade-long battle with the disease, he became an instrumental voice in the ALS community. He helped to create the California ALS Advocacy Committee, whose work resulted in the passage of 2 bills, the ALS Standard of Care Bill, which stated that the highest standard of care for people with ALS in the California Health Code and the California Tax Checkoff Bill, which to date has raised more than $600,000 for ALS research. In addition, along with other advocates, he helped secure a pivotal $18 million grant for ALS research from the California Institute for Regenerative Medicine, CIRM. The ALS Association and the Golden West chapter recognized him for this work, honoring him with the Iron Horse Award in 2010 and the Heroes Living with ALS Award in 2011 and again in 2016. A major outcome of Jim's work was the formation of this California ALS Research Network in 2010 and the creation of the annual California ALS Research Summit in 2011. Jim was very unique among my patients in that we would spend the majority of his patient visit not talking about him at all or about his ALS disease, but talking about what needed to be done. He wanted to know, what do you need? What do you need as a doctor? What do patients that you see need? What do researchers need? He always wanted to help others, and that was his focus. And he continues to be a huge inspiration to me. And so I've shared a little bit about him, but now we'd like you to watch this video to learn a little bit more.
Whether it was from his years playing football at the University of California, Santa Barbara, his military service as an Army captain in Vietnam, or his 30 years as an attorney, Jim Barber understood the importance of working together towards a common goal.
Successful teams involve people where everybody on the team puts in more than they take out.
It was no surprise to family and friends that he would turn the news of his ALS diagnosis into an opportunity to help others.
You could see that something had to be done because the progress was not being made, and one way avenue was through the legislature.
My name is Jim Barber. I have ALS. I'm here today with my wife of 43 years, Cheryl, without whom I would do absolutely nothing these days. This disease is a toughie. Research is the only way out. We need some help.
The motion is to pass. The amendments will be taken in appropriation.
Jim worked tirelessly to advocate for ALS research funding beyond the state legislature. He offered key testimony to help secure a pivotal $18 million grant for ALS research.
I feel we're in good shape with this particular proposal to make that happen after 10 years of work.
We all have hope, but hope is not a strategy. Working with people like Dr. Svensson is a strategy.
I've waited a long time to be able to say yes to this.
Jonathan Thomas.
Yes.
Art Torres.
Aye.
Dr. Svensson, congratulations.
Jim and Cheryl participated in many public awareness and community outreach events. In 2015, Jim's family took the ALS Ice Bucket Challenge in his honor. Jim's most visionary and enduring work was the creation of the California ALS Research Network. The active work group hosts the annual California ALS Research Summit. His passionate efforts to advance research, patient care, and public policy initiatives are his lasting legacy that will benefit the ALS community long into the future.
Jim would want you to continue all that you do. ALS awareness, research, patient, and caregiver support. A cure was not found in his lifetime, but progress has been made. So please keep up your good work, and thank you.
All right. Well, I also want to thank Cheryl Barber, who's watching tonight. That was a wonderful introduction to Jim. Those of you who knew him, he knew he had a deep passion and commitment to the mission of the Golden West chapter. And it was his desire that the ALS Research Summit would encourage collaboration and sharing of ideas, as well as give special recognition to emerging researchers. So beginning in 2017, and now annually, the Barber Family and Golden West chapter is presenting 3 cash awards of $1,000 each to each of the top poster presenters, along with a special memento recognizing their accomplishment. And you can see the memento there in the center. Now, posters are research presentations that are made by young investigators at the meeting. Everybody can go along and see it and discuss it. So these awards are announced before the conclusion of the summit. In addition, the winners are formally acknowledged and have the opportunity to participate during an educational event for the ALS community, which is this one. So let's go ahead. These are the snapshots before of previous researchers, and these are the ones that have won it up from 2017. So now it's time for a drum roll to announce the winners for this year. So we have the next slide. And here they are. So the research award winners this year were Michael Ramos, Monica Fioli, and Carolina Rangel, Korndorfer-Rangel from UCSD. The other 2 candidates who won the award are from Cedars-Sinai. And so a big round of applause for the winners this year. So on Zoom, you just applaud yourself, but I'm sure everybody else was also clapping. And I think now we're going to actually have a bit of fun. Every year, we just talk to the 3 winners and find out what they've done. And I try and put it into some context for all of you listening out there. And I love this because the energy that you get from the young people doing this research in ALS is always very important. And I always tell this story, but nobody really knows who. Watson and Crick discovered DNA is maybe one of the biggest discoveries of all time. I always ask people, how old do you think Watson was, Dr. Watson, when he discovered DNA? And people are always like, oh, 45, 50. No, he was 28. Discoveries happen, big discoveries, when you're not scared to think out of the box. And that does old people push us aside and get these younger brains onto this problem of ALS. So I'm not sure where we're starting, guys, but we're going to start with Michael, or did we have a sequence? In that case, I will do the sequence. Michael, do you want to start? And then we'll go to Monica.
Sure.
And then we'll end up with Carolina. How's that?
If I can start and just share my poster.
Okay.
All right. So this is the development poster. SOD1 G93A ALS disrupts development of G networks and accelerates aging in mice, microglia, and motor neurons. Now that might seem like a big mouthful, but basically my research, what we want to figure out is what is exactly happening in the spinal cord during ALS pathogenesis. Because for most of the ALS research that's happening right now, mostly deals with end stage of the disease after the disease has run its course. But we want to actually know what's happening and what's kind of what is the dysfunction that's happening throughout the lifespan of the disease. So we want to know what's happening to each individual cell types, because your spinal cord is composed of not just neurons, but also a lot of different supporting cells like astrocytes, microglia, oligodendrocytes. And it's only in the recent few decades that the contribution of those other cell types have been appreciated in the course of ALS. So our approach is basically to just throw money at it, so we use a technology called single nucleus RNA sequencing to figure out what is happening to all of the genes in all of the cell types in the spinal cord that we collected throughout the lifespan of the mouse, the healthy mouse, and the ALS mouse. And this ALS mouse that we use is very well known. It's the SOD1Q93A mutation mouse. And what we found is that the cell types that are most affected in ALS and spinal cord are these astrocytes and microglia. And they are the ones that are actually experiencing some form of dysfunction early on in the disease. And this is important because if we can see what is happening early on, then that is something that we can measure in these cell types. So this could be another metric that we can look at during, let's say, to figure out if a new drug will, for example, slow down or halt disease progression. So that could be a useful thing, or it could be a source of new targets, let's say. So we came up with a list of genes for both microglia and astrocytes, and what we found is that the dysfunction that happens at the end stage of ALS converge, meaning that they are the same pathways that are being dysregulated in aging. So what we found in short is that ALS accelerates aging, accelerates healthy aging. So I think that's where I'm going to end this, and I'll be happy to answer any questions. Thank you.
Michael, good overview. And I think we all know that as you get older, you're more likely to get specific diseases. And this could be common for Parkinson's, for Alzheimer's. And I think understanding how that aging intersects with ALS is going to be very important. And I think maybe certain genes are, being dysregulated in aging that are triggering the ALS, right?
Yes, definitely. That's something that we also are trying to look at.
And in the brain, we have a number of different cell types. We have neurons, which we always think, the motor neuron, which is making me move my hand now, that's really important, right? But there's a cell around it called an astrocyte. It's even more important, that controls and monitors the health of the cell. And I think what we're finding is those astrocytes and other types of cell in the brain can be dysfunctional, again, with aging, that then triggers the motor neuron to die. So the kind of work Michael's doing is going to sort some of that out. Any other last thoughts, Michael, on your project you want to relay?
It's just that there's a lot of exciting stuff that I'm finding, and that hopefully I'll be able to share that soon.
Yeah, and the genes that you see in changing there, that's called a target. So if Michael discovers something that's changing, the pharmaceutical companies over at the meeting will pick up on that, and they'll say, oh, wow, it's a new target. And then boom, you get another drug developing for ALS. This is where it all comes from. All right, let's switch to Monica to present your poster, Monica. I've started my stopwatch here for everybody.
Okay, I hope everybody can see my screen, and good evening, and thank you to the Barber family for addressing me with this award, and thank you, Clive, and everybody for having me here tonight. So my work it's like a little bit different, I would say. It's not like right now searching for a specific therapy, but eventually to more identify a new target, because as we know, TDP43, as Clive was mentioning, is accumulated in many of the cases of ALS. And this protein is not only like contained inside the nucleus of our neurons, but it's also outside in the axons. And the interesting things is that our axons, they can like extend for very long like distances. And so proteins like TDP43 and many others, they can be transported along these axons thanks to these motor proteins that you can see here in this image. So in my case, I'm like trying first to understand how, let's say, this car is working, right? So try to figure out how, in this case, TDP43 is moving along the axons. And so how then this mechanism might be disrupted during the disease. And so in my case, what I try to do is to see how physically TDP43's movement, as you can see here, evidenced by this arrow, the particles of TDP43 moving, and I compare its movement with other like cargos and so proteins that also move along the road, okay, that it's like extending along the axons. But most importantly, I'm trying to establish what are the interactions of TDP43 with the motor machinery, because this will help us understand if during the disease, like it happens, for example, also in other diseases like Alzheimer, the axonal transport is disrupted. And so if the accumulation actually of TDP43 might be a consequence of a disruption of this interaction with the motor proteins. So my next goals are actually, and this is like part of the work that I'm doing here in the lab of Dr. Svensson, so to figure out if this behavior of TDP43 is altered in stem cells from patients affected by ALS.
Thank you, Monica. You might notice, the more astute of you might notice that Monica is actually currently in the Czech Republic. And like she said, she's visiting my lab. This is the wonderful thing about science. It's research. It's going across the spectrum, and we love to collaborate internationally. So Monica, TDP43 is a very interesting molecule. What do you think? Why do you think it causes? Why do you think it's related to ALS? Do you have any ideas? And you're testing like why it would cause these motor neurons to die?
Well, the thing is that, as we know, TDP43 is involved in the regulation of like the homeostasis of RNA, and we have RNA inside the nucleus and RNA, in particular the messenger mRNA outside, so in the axon, as I was mentioning. And because like these mRNAs need to be translated in proteins, and this can happen also at a very long distance, so far away from the nucleus, I think it's fundamental, the action in this case of TDP43, to carry these mRNAs and, for example, ensure that there is like a good synaptic activity at the end of the axon terminal. So in this case, at the neuromuscular junction, so that all the factors that need to sustain the communication between the motor neurons and, for example, the muscles, they can be delivered in the proper way. And axonal transport is like one of the most important processes that allows all these cargos, all these, let's say, boxes like Amazon, trucks can deliver. The same happens with the motor proteins and TDP43 binding the mRNAs.
I like that analogy with Amazon. You know what happens if Amazon goes down, you don't get your package? That's what happens.
That's the point. That's the point, exactly.
So if the axon doesn't work, the end of the axon doesn't get its package and the neuron doesn't function. Beautiful work, Monica.
Thank you.
Congratulations on the award, both of you. And the last speaker today from this set is Carolina from UCSD. So you're on mute, I think, Carolina. This is the meme of the century. You're on mute.
Hello. Now, yes. So yeah, thank you so much for having me here today as well. I'm very honored. And I'll tell you about my project at UCSD with Don Cleveland's lab. So TDP43, as you're already speaking, is misregulated in ALS, and it leads to the loss or misregulation of other many genes. And one of these genes is called STATMIN2. It's encoding the protein STATMIN2. And this protein is very important for axon regeneration. And actually, it was proven by reducing TDP43 and seeing that the axon couldn't really regenerate after injury. But when you add only STATMIN2, that is only one of the more than hundreds of genes that are deregulated by TDP43 pathology, you could recover the axon regeneration capability. So our group became very interested in this protein and trying to understand what is the mechanism. And in my project, what we did was growing these neurons, motor neurons, derived from iPS cells, and try to validate a method to understand differences in gene expression when STATMIN2 is there or not. So which genes would be more or less expressed when STATMIN2 is absent. So here we did all the validation, showing that the method was efficient. And then here we can see all the genes that we found. So we found many genes that are differentially expressed when STATMIN2 is not there. So it really shows that somehow, directly or indirectly, STATMIN2 affects gene expression. And this is very important because then we can use all these genes and see if they are part of a root that regulates something. And we actually saw that it's part of cell adhesion. Many of these genes are part of the cell adhesion pathway. And it makes sense because when the axon is growing, it needs to adhere to touch other structures and try to stretch out to find his way. So it's very interesting. And yeah, in the future, we want to keep understanding better these genes and try to understand STAT-MEA2 mechanism.
Beautiful, beautiful work. It's amazing that this TDP43, this horrible name for this, it sounds like tar or something, but it is like, stuff which leaks out of the nucleus and then activates things which mess up other proteins like STAT-MEA and doesn't allow them to function. And by understanding that, we can start looking for ways to enhance those things that TDP is messing with and affecting. So what do you think? I think some ways that you could do this in the clinic. Is anybody thinking about how to activate STAT-MEA in a clinical trial that you know about?
What I know is that some people are studying ASOs to try, because the problem about STAT-MEA2 is that it's not expressed because TDP43 protects a region in the transcript that is not gonna allow the translation of this exon 2. It's a cryptic exon. And so they're using ASOs to try to mimetize, to be the same as TDP43, to bind there, and then allow the correct transcription of TDP43. So yeah, that's what I know about clinical trials for STAT-MEA so far.
Yeah, very, very similar to spinal muscular atrophy, right? Where they use ASOs are antisense oligonucleotides, a horrible name again, but it's just a way to, it's like putting a little template onto the DNA of your cell. There's an error in your DNA, and then you stick this thing on it and it skips over it and reads through it. So it produces normal protein. And that technology is in the clinic for a disease called spinal muscular atrophy, which is like a baby version of ALS. And young kids, it's very sad, go completely paralyzed. So maybe we can use that for STAT-MEA and understand, how to get it to be produced normally.
Yeah.
Very exciting, guys. Look, fantastic posters. We have a few more minutes. I'm just going to go around just for a minute response from each of you, a little bit about sort of why you got into ALS. And I'll go Monica first. What was it that really drew you into ALS research, or was it an accident? And maybe tell us a bit about the interactions you had at the poster at the meeting.
Well, my inspiration actually started by looking at the tenacity of an Italian researcher, Rita Levi-Montalcini. That's how I entered first in neuroscience field. I mean, it was really inspiring how even during the Second World War, she was able to, keep on going with their experiments, build up a lab in her bedroom and moving on. And I had the honor to know and have as my teacher in biochemistry at university, a professor that was working with there, and she was really interested in ALS research. And she had a SOD1 model in her lab. So since my master's degree, I have to say I entered into this research. And so from my thesis on, I continued pursuing this kind of field because it was of great interest, and also because I think it turns the resolution somehow, or new findings that can help all the people to have new hope and more time for their life.
Yeah, I think we all inspired, and Levi-Montalcini was an inspiration for many, many generations of women in science, just like Madame Curie before her and others. And so fantastic. Michael, what got you into ALS research? And I know you're in Richie Ho's lab who's doing it, but did you have an interest before you came to his lab? Or?
Well, I don't know if you remember, but I used to work for Drew Sareen, who also used to work in ALS. So that's kind of I was a technician in his lab, and I was in charge of many different projects in there. And one of them just happened to work with ALS. So that's kind of my introduction into the ALS field. And from there, I just figured I really want to keep doing this kind of research. So I joined the PhD program, and now I'm in Richie Ho's lab doing this kind of ALS research.
Yeah, and Drew Sareen is a wonderful person. He came with me from Wisconsin when I moved to Cedar Sinai originally, and has a great lab. And Yeah, I think that's what I love about this research area is even if you're in a technician in the lab, you get the bug for research, and then you see the ALS patients and it really drives you into that area. Can I do something to help and understand more about this disease? And before you know it, you're in a PhD program, and then you're a young professor, and then you're really moving ahead. But it's an inspiration when people like Jim Barber and Golden West chapter, and when you, like at the dinner, you meet patients, then you really feel we've just got to, put all our energy into understand this disease more. Thank you, Michael. So we're going to finish up with you, Carolina, why you got into the research. Don Cleveland is a king of, I remember Don Cleveland, your boss is amazing, because I first knew him for ALS and I thought, oh, he's a fantastic ALS researcher. And I do a lot of research. I went to a cancer meeting and he's there talking about cancer. And I got him after. I said, Don, what are you doing talking about cancer? You're an ALS expert. And it's, well, I dabble in cancer. And he's a world expert in RNA metabolism in cancer and a world expert. Yes. Anyway.
Yeah. So for me, I always loved chemistry and biology, and so I decided to do my bachelor's in pharmacy back in Brazil, where I'm from. And I received a scholarship from Brazilian government to go to the Netherlands. And I went there, and it was a research exchange. So I worked for 10 months in a lab, and they study Huntington there. And I just really fell in love with researching this kind of diseases. And then when I went back home, I studied ataxiatry or Machado Joseph. And it was really interesting for me how these proteins can aggregate and if they're toxic or if they're protective. And yeah, I started my master's in the Netherlands. Back then, I worked with Pasterkamp with ALS and epilepsy. And yeah, I was checking some papers that I found interesting, and I found Don. And yeah, I entered in contact, and it was the best choice I've ever done. And yeah, I remember back in the Netherlands, we also had a class with patients, and it was really important for me to decide that I wanted to continue doing research in this field. So yeah, that's it.
It's thanks so much, Caroline. And I think all of us, if you meet a patient with ALS, it really impacts everybody because of the severity and the cruelness of the disease. And so we're all in the same place. We're all trying to understand more about it. And thank you both, all of you, for your presentations and all the work you're doing. And I'm going to hand back now to Dr. Lohmann-Herth to take over. Dr. Lohmann-Herth.
Thank you so much. I appreciate what you said, Clive, in your last sentence about when you meet a patient with ALS, it sticks with you. There were 3 patients in my neighborhood growing up who had ALS, and that was one of the things that inspired me to go into medicine and to focus my career on ALS. So today, in the next few minutes, I'm going to take you on a whirlwind tour of diversity, equity, inclusion in ALS research and care, and talk about some practical ways we can improve our diversity. Next slide. I want to give particular thanks to Dr. Mark Terrelong, who's a faculty member in my division at UCSF, who did a lot of the research on pulling some of the papers around health equity and research that I'm using in this talk. Next slide. So what do we mean by DEI, diversity, equity, and inclusion? So diversity refers to those unique characteristics, perspectives, and life experiences that define us as individuals. And then inclusion is about creating an environment where all individuals contribute fully and feel valued, engaged, and supported to reach their full potential. And then equity is about having fair treatment, access, and opportunities and advancement for all individuals. Next slide. So what are some diversity characteristics? We have age, race, gender, ethnicity, sexual orientation, wealth, religion, so many different things. And interestingly, sometimes people, all these various identities can intersect with each other. For example, one of the faculty members that I work with at UCSF, he's a Black man who grew up in a very rural area, who you might expect would have had some adversity in terms of getting to where he is today. But he was very, very wealthy, from a very wealthy family. So went to the best boarding schools, the best colleges, and he would acknowledge himself that he has had very little discrimination because of the wealth that kind of counteracted some of these other characteristics. Next slide. So how do we think about increasing DEI, both in research and in clinical trial selection? And I'm just going to briefly give you an overview of some of the challenges and opportunities that we have. So we obviously want to have good access to healthcare for everyone. And there's things that we can do on the physician or healthcare team to help with that, and then things on the patient end that can help with that. So on the physician end, looking at the top, we want to think about, are we approachable, accessible? How are we affordable? Is the care appropriate? And then on a patient end, the patient's end, there's can sometimes be issues around ability to pay, ability to engage, ability to reach the healthcare that they need, ability to perceive the opportunities. So there's work that needs to be done on both ends of the spectrum to try to really help improve healthcare access. And this came up front and center with COVID. So we've all seen the issues around access to healthcare and some of the racial differences there. So this is a quote from an article talking about access to healthcare, and it says, elderly women, children, racial and ethnic minorities, social economic disadvantage, and individuals with chronic health conditions experience greater specialty access challenges and poor health outcomes, particularly in medically underserved urban and rural areas. Next slide. Well, let's look at California. What's happened to our demographics over the years? In the 70s, California was 76% white. Today, it's 35% white, 39% Latino, 15% Asian, 5% Black, and then a growing percentage of 2 or more races. Well, the people that I work with at work do not look like the demographics of California. And what we would really like to see is a healthcare team that looks more like this picture, really reflecting the diversity that we have in California, as well as the patients in clinical trials. So speaking of clinical trials, the NIH in 1993 specified that in any type of research, clinical research, that there needed to be outcomes by race, sex, and or ethnicity. And that women and members of minority groups and their subpopulations must be included in all NIH-funded research. Well, a group monitoring this published a paper in 2018 entitled "The More Things Change, the More They Stay the Same," citing that NIH policies have not resulted in a significant increase in reporting results by sex, race, or ethnicity. Papers are good about reporting the demographics of their population, but not the connection to the outcomes that it really is needed. Next slide. So why is it that we don't have a more diverse research population and clinical care team? Well, one thing that was found is that part of it is lack of mentoring. After controlling for applicants' educational background, country of origin, training, previous research awards, publication records, and employer characteristics, Black applicants still remain 10 percentage points less likely than whites to be awarded NIH research funding. Next slide. So what could some of the reasons be for this? Well, one of this is implicit bias. We all have implicit biases, just that tendency to automatically associate people with certain characteristics based on the stereotypical characteristics of the groups into which they're placed. A bias that I have when a patient says, I need, my records are at Dr. Jones' office, and I'll automatically say, well, tell him to send them over here. Here's my fax number. And the patients will sometimes correct me and say, why are you assuming my doctor's a man? You're a doctor, you're not a man. And it's that implicit bias because of when I trained that most of the physicians were white men, and I still carry that bias with me. And so I need to recognize that and compensate for that in my language. And there's just many other examples of types of implicit bias. So I'd encourage you to do the free tests online to learn where your own biases are. So I showed that scale in the beginning about diversity, equity, inclusion. And why is it tipped? Why is it that we've gotten the numbers up? There's fantastic diversity of medical students coming into medical school. California has become very diverse. Why aren't we seeing diversity in our clinics and our clinical trials and in our care providers and researchers? Well, a lot of that is around belonging. So one of the things that I learned in my role mentoring students is that many students do not feel that they belong at UCSF. And why is that? Well, first of all, security is more often to basically card a student of color as opposed to myself as a white woman. Half the time I will forget my name badge and I can waltz right past security, no one questioning me that I don't belong there. But for a student of color or a faculty member of color, they're often carded every time, and not just by security. Sometimes it's other faculty members or researchers, say, working on the weekend. They'll question why that person is there. And so belonging is something that we're working very hard to try to make sure that that people are treated equally, that they are accepted, and that they feel that they belong in that environment. So thinking about patients now, what are some barriers to participating in clinical research? Well, the cost of performing the research can limit enrollment. We oftentimes don't have funding to fund patients to have more visits done in the home, for example. Patients are often required to come physically into the medical center in order for us to get paid to do this study. It can be hard for patients to even know that studies exist, or getting an ALS diagnosis in time to be able to participate in research. There can be a language barrier. Long travel distance from the study site, being away from family support. There can be skepticism about research because of prior harm done, and particularly the Black community. There can be problems with having availability of interpreters and translators to translate the study materials. Limited study resources, I already mentioned. Lack of local medical support for non-study needs due to insurance issues if patients are traveling from, say, another country to come and participate in the research study. And then difficulty getting acquainted with new electronic health systems. A lot of our communications now all electronic, and people aren't always as tech savvy. And then barriers with health literacy and scientific literacy can also make it difficult for patients to understand the importance of participating in clinical research. So how can we improve the diversity of recruitment? One of our faculty members, Dr. Laura Rosso, has been thinking a lot about this, and she's created some practices in our group that have helped to improve our diversity. One is to have coordinators attending our satellite clinics, making patients aware of research opportunities, translating recruitment documents, providing transportation and lodging for visits, allowing home visits whenever possible, providing telemedicine equipment, such as a Chromebook for patients who don't have access, and then making it sustainable, trying to think about how can we increase our clinical trial revenue through improved recruitment and negotiating higher budgets with clinical trial sponsors who are also motivated to try to improve the diversity of our patients. Next slide. So I'd like to tell you about a success story. This is a patient whose name I've changed for confidentiality, but Jose was a newly diagnosed, rapidly progressive, non-English speaking patient from Mexico City who wanted to be a part of an ALS clinical trial. And he did have several advantages. His wife spoke English and did a lot of internet research, and she was able to find that we were doing something, the Healy trial at UCSF, which is a trial that is based at Mass General and is a really nice trial with a very favorable placebo control ratio. And so she found this trial and she contacted us and said, what would it take for him to be able to come and participate in the clinical trial? And so what we did is we talked to the head study and we said, do you really have to be a US citizen to be a part of a clinical trial, or would it work if he came and he had friends in the area that he could stay with? And they said, okay. And we worked to translate the documents. And he's successfully completing a clinical trial at UCSF, despite not having insurance, not speaking English, and being from another country. And so these are the sorts of stories that we want to make more common. This is our very first non-English speaking patient enrolled in a clinical trial, but we would like to have more patients that reflect the diversity of California. Next slide. So how can we further increase DEI and access to clinical care? Next slide. So just talking a little bit about healthcare, obviously patients need to be seen clinically in order to hear about clinical trials. They need to have an earlier ALS diagnosis. And that all happens in tertiary care centers. Next slide. And if you look at the US population, most of the US counties are rural, particularly in the Midwest. Next slide. And so what are some of the difference? Well, even in urban settings, there can be increased poverty rates. Residents may be more likely to be foreign born, may not speak English, less likely to own their own home. And in rural areas, which is really 1/6 of the total population in the US, only 1/10 of physicians practice in those regions. Patients are often older, more likely to be uninsured, and have less education, which makes it more difficult to access treatments. So the rural population, it represents a large proportion of our country, and yet these patients have significantly longer travel time to clinics and trial visits, and there's just aren't a lot of trial locations available in rural areas. Next slide. And then the main point about this slide is if you look at the very bottom line, the dark blue line, that is the physicians that work in rural populations, and then the lines above are physicians that work in more metropolitan areas. And as you can see, there's just very few physicians in rural areas. Next slide. So how can we do better? Well, we have the satellite, the blessing of satellite clinics that the ALS Association funds in Fresno, Monterey, Santa Rosa, and Modesto, and then soon to be Santa Barbara. And we have this ALS Think ALS tool, which is on the ALS Association website, which helps non-ALS specialists think about ALS, think about referring. Next slide. And so when you think about the access to ALS multidisciplinary care, travel time is very high. There's we ideally want patients to have 2 to 4 visits per year, and then to see the full multidisciplinary team. Next slide. And so when Dr. Jill Goslingo, who's another faculty member in our group, very interested in studying underserved populations, she found that non-white ALS patients may need extra support. And so this compares non-white versus Caucasian patients, with the non-white patients being in blue, and then the white patients being in I'll just go on to this next slide. But basically, satellite clinics improve access to ALS care. So patients who are have access to a satellite clinic definitely get care more readily. But even those who are within 200, who live further from any type of clinic, satellite clinic, or one of our main clinic, really struggle with not getting as frequent visits, even with a virtual visit. Next slide. And so in Fresno, where Dr. Mark Terrelong is really focused on working, and where we have 4 satellite clinics per year, the patients seen in clinics still don't reflect the diversity of Fresno. So 3/4 of those patients are still white, whereas the diversity in Fresno is greater. And so we want to continue to work to help our clinics look more like the populations that we serve. Next slide. And so we're working to expand these clinics, and part of that work involves training fellows and residents in the Fresno area to try to develop a pipeline of providers in that region. Next slide. And I mentioned Santa Barbara, which we're excited to be starting a new clinic later this year. Next slide. So in summary, we are going to be, we're working to overcome barriers in research and care with our virtual clinics by trying to work hard to educate all of our ALS patients, regardless of where they live, about clinical trial opportunities. We're working to create a more diverse clinical and study team. And we're most importantly connecting patients with a local Golden West chapter care manager who can help guide them through the process of access to both clinics and clinical research. Next slide. So thank you. It's only together that we can work to defeat ALS.
Thanks, Kathy. Fantastic overview. And I think we're going to move to me, and then we're going to finish up with Dr. Lemonhead and I asking and answering questions. So shifting gears a little bit now and moving on to this approach that we've been developing for a number of years. And Jim Barber, actually, in the video there at the end, if you saw him talking about the new funding, the $18 million, that's really what started what I'm going to tell you now. All that time ago, because of Jim's advocacy and the Golden West chapter's advocacy, this project. So I'll have the next slide. So obviously, don't need to go into this in too much detail. We know that there are no real drugs for ALS that do much better than 3 or 4 months of expansion of lifespan, which is definitely not a cure. We need more. We know that there's genetic forms of ALS that I've talked about, which there is some hope for gene therapy approaches for those. But really, the other 90%, if you don't have a mutation, it's very difficult to look at those diseases because, as I've told you, we don't know the cause exactly. And so new drugs and therapy approaches are desperately needed. The next slide. So we, some time ago, had an idea that we could replace these protective cells in the brain. I think if you were listening to the poster presentations earlier, I mentioned in my discussion, I think with Michael, that although the brain has these motor neurons, which are critical for function, that they are dependent on support cells. And these support cells are called astrocytes. And we thought if we could replace those support cells in the brain and the spinal cord, and first we thought the spinal cord, that's where the bottom motor neurons die, that we could slow down the degeneration of the motor neurons. And at the same time, there had been drug developments, a growth factor, which is a hormone that we know can actually protect motor neurons, have been developed, called GDNF, or glial-derived neurotrophic factor. So we had these two pieces of the puzzle. Here's a growth factor, and here's a stem cell making an astrocyte. This astrocyte's in the spinal cord or the brain. And we tried both independently, and neither seemed to work too well on their own. But when we combined them, that was very powerful. Now, GDNF, you can't get into the blood-brain barrier, so we need to develop a way to get it in. So we engineered some stem cells to make the protein GDNF, and that's in green there, those little balls of cells. We then implanted them into the spinal cord, the big arrow there, into the spinal cord of patients. And I've got the Trojan horse because it's like a Trojan horse. And in the Egyptian times in war, the Trojan horse would be wheeled into the castle and the troops would get out. Well, we actually wheel in using stem cells, we get the GDNF in, and then the GDNF's released from the stem cells in and around where the motor neurons are dying. So it's delivered directly to the spinal cord, whereas you can't normally get GDNF in there. And so on March 17th, and way back in 2016, following a huge amount of work, started off by Jim Barber's award that that CIRM, the state gave us. And CIRM is the California Institute for Regenerative Medicine, guys, Prop 14, that's providing $5.5 billion for stem cell research in the state of California. And CIRM has supported this work from the very, very start. In fact, before that, the ALS Association supported it. And so this is a combined effort from the state and the Golden West chapter, and a long series of projects and research has led up to this trial. So we've just completed the trial where we transplanted these cells into the spinal cord, and I'm going to show you a little data from that now. The next slide. We published this recently in a paper, and you can go read the paper. Just blast it up on your screen. I'm not in control of the slides, so when I say next slide, maybe then that's when you go to the next slide. It'll be easier. So the paper that just flashed up, actually, can you go back, actually? Thank you. Was published recently, and these are the people involved, the collaborators. Bob Bailo is a neurologist, Pat Johnson is the neurosurgeon, and Pablo Avalos does everything in terms of coordination of the trial. And this trial showed that we can transplant these progenitor cells. They make GDNF, and they were safe in this patient group that we did, 18 patients with ALS. Next slide, thank you. We tested in this machine, some of you may know, is an isometric test of muscle strength in patients. So the patients would visit the clinic every 2 or 3 months. to get a test of their strength. And just don't worry about this graph. That dotted line, it was a kind of unique trial. We only put the stem cells on one side of the spinal cord. So we're only expecting to see an effect on one leg. And so what we did is we tested the non-treated leg, the left in some cases, and then we tested the right leg, the treated leg. And then if that dotted line, if that mark is on the dotted line, it means there was no effect. If it's above the line, it means the leg that we treated was progressing slower. And so you can see there in the dark blue, which is a higher dose of stem cells, we saw an effect where in every case, the leg that was treated was doing better than the leg that wasn't. Now, this didn't reach statistical significance, and this trial wasn't designed for that, but it did tell us that the process is very safe. We can do this in patients with no detrimental effects, and the FDA has now said, oh, it's a safe trial. We can go back and do more patients slightly earlier in the disease and with slightly different targeting. The next slide. The next slide. And when I say targeting, this is the spinal cord. Next slide. And this is the targeting. And we were able to collect the spinal cord from patients who passed away and they donated their tissues. We could actually find where the transplant was in the spinal cord. And this is one transplant here. And in brown, you can see in the spinal cord GDNF. This is, we stained for a particular marker that tells you that the GDNF is being made in the spinal cord of this patient. So this trial really proved that we can put the stem cells in, they can make an astrocyte, and they can secrete GDNF. So these are now young astrocytes, new cells in the spinal cord of this patient that are pumping out GDNF. And we feel that this is very important because now we can move ahead in more patients knowing that these cells can survive and release GDNF, and in some cases up to 3 years. Now you have to have immune suppression at the beginning of this trial, but after 1 year, we stop the immune suppression, and it's basically no drug treatment. The cells are in, they're producing the GDNF for you, and they'll survive as long as you do. The next slide. So the conclusion, and the first treatment was safe. Next one. I'm just going to run through these bullets. Just to say there was in the spinal cord a little bit of pain in some patients, which could be treated with gabapentin. This is because, and I'll show you in a moment, the targeting in these first patients was a little too high, and I'll show you why in a second. We saw some benign neuromas, which means a small lump forming on the side of the spinal cord in some patients, but that wasn't serious and didn't cause any issues. All the patients that came to postmortem did have grafts surviving, and that was 11 patients. We saw the grafts survive, so we know it can work. The cells could get in. They didn't quite migrate as far, and that was one of the surprises for the trial. They didn't migrate into the area we wanted, and I'll tell you how we're going to mitigate this in the next trial in a moment. Next one. So here's our targeting, and when the FDA allowed us to do this, this is a cross-section through the spinal cord. So the middle is where that red blob is the middle of the spinal cord. The top is sensory area, and the bottom, you see those black dots down there, they're the motor neurons that die in ALS. And so we decided at the beginning, we target the middle, and we hope that the cells would migrate into that shaded red area at the bottom, down into where the neurons are that are dying. What actually happened is in most of the patients, the cells didn't migrate down. They stayed exactly where that red dot is. And in some cases, they went up and got stuck in the top of the spinal cord. And that's what we think caused some of the pain that some patients felt. The next slide. So in the new targeting, we're going to be going a little deeper. And now we know we can get safety because in some cases, we did go a little deeper. We can slide that. The cartoon's not working, but that pillar will go down deeper, and we'll see if we can get the cells into the very area where we need them, which is where they die down there in the base of the spinal cord. So that's something we're setting up now in a small patient trial. We're still waiting to get IRB approval to move that trial forward, but that's our next goal with this project. Next slide. So we hope that this combination of deeper targeting, going slightly earlier in disease, like I mentioned earlier, in patients, the first trial we did, the FDA said we have to go late, but now we're allowed to go a little earlier, and we hopefully will see some protection of those motor neurons, and that's very exciting. Now, in addition to the lower motor neuron down there, number 1, which we're trying to target, in ALS, as I think all of you probably know, there are 2 motor neurons involved. And to be called ALS, you have to have both effects on the bottom motor neuron there in the spinal cord, and this is the one that goes out to my legs. There's a second motor neuron up in the top of your brain up here called the upper motor neuron, shown in the red line at the top there. And we also know that motor neuron dies as well. So in the long run, even if we can show we can protect your lower motor neurons for some time, we think that the upper motor neuron will die as well. So you'll have your lower motor neuron, but we need the upper motor neuron to activate the lower motor neuron. So for some time, 3 or 4 years now, even halfway through the previous trial, our team decided to investigate whether we could do something for the upper motor neuron, because that we need to correct as well, if we're going to have any hope of long-term effects in patients. So next slide. Gretchen Thompson, when she was in my lab, did a lot of work, and a lot of other people around Gretchen, this team, asking whether we could put same cells, the progenitor cells making astrocytes that secrete GDNF, this product that we developed, into the motor cortex area, and what would it do? And this paper shows you that actually when we do this, and this was funded by ALS Finding a Cure, also some of the DoD actually funded some of this work, and ultimately CERN, but we actually said, we'll just transplant the cells now only in the motor cortex and see what happens. So the next slide. And we can actually get GDNF expressed nicely. This is a section through the rat brain. And that strip at the top there is the part of the rat brain called the motor cortex that controls movement. We got the GDNF cells in there. They made astrocytes, and the astrocytes embedded themselves in the dying motor neurons. And this targeting was actually easier than the spinal cord, because the brain is actually easier to target than the base of the spinal cord. And there's good targeting ways we can use in patients I'll show you in a moment. So we delivered it there. The question is, what happened? Well, if you look at the red line there, that is the treated group, and the black line is a non-treated group. And down is worse. And so I think just look at that first data for the BBB score, which is a behavioral score. We've delayed the progression of the disease by just putting these cells in the upper motor neuron area. So this was very strong evidence that putting the cells in the motor cortex could protect not only the motor neurons that we saw, but also slow down disease progression in this animal model of ALS, the SOD1 model. Next slide. Now we have to move to humans. That's always a huge move. The human brain is one of the most fascinating structures, and it turns out you have two brains, all right, two sides of the brain, but also within the one side of the brain, you have two areas of, and it's called the homunculus because it represents the whole body. And there's two sides of this area on each side of your brain, two sides. One is a sensory area, and the other one on the right is called a motor strip or motor area. Motor means movement. And each, and on that pink strip, you represent different parts of your body. So very top of that pink strip is your toes and feet. And somewhere in the middle, that little knob area is your hand. And you can see the representation of the hand is actually very big, because for our hand, we have to have a lot of motor control. And so the brain devotes a lot of attention to the hand and a lot of neurons, because we need to have a lot of dexterity and movement in our hands. So we decided that we'd focus on the hand area, because we can't transplant that whole area right now, although we could transplant a wider area if we get safety in this study. So we chose to do the hand, what's called the hand knob. Next slide. And this is just another way of looking at a slice through the motor cortex and showing that little knob there at the end that says hand and wrist. That's the area that we're going to target in the brain. Next slide. Now this involved a different surgical team. We also got funded by, again, CERN. Following on from, again, Jim Barber's original award, we got a further 12 million to do this trial. Next slide. Supported by the state. This is the identifier. I'll give this again at the end of the talk. We're currently recruiting for this trial. The PI is Rich Lewis. Pablo Avalos is coordinating the whole thing, who you can contact if you want more information. I'll give his email at the end. Adam Mamalak is the neurosurgeon, and I'm the sponsor of the trial and the PI of the grant from the state. This is our operations. This is called the clinical protocol. We want to show safety. You have to do safety again now up in the upper motor neurons, as we did for the spinal cord. We're going to have these astrocytes secreting GDNF. There's going to be 16 patients. Again, safety. There's MRIs that you have to have and some lab assessments. We'll be doing muscle strength again with that machine I showed you, the Atlas handheld dynamometry, which means strength of the hand. And this 9-hole pinch test, but also a 9-hole peg test where you take pegs out of a little grid I'll show you in a second to look at how the hands are affected over time. And we're only going to do one side of the brain for safety first. And in your brain, actually, it's interesting that the left side of the brain controls my right hand. So we'll be looking at the effect of the cells on your right hand and the left hand over time and seeing if the cells can slow down the loss of function in one of your hands. And that's the first part of this trial. Again, it's safety, different doses of cells, and you will need immune suppression for the first year, and then you can come off the immune suppression. Next slide. There's a couple more slides left and I'm done. We can go to questions. Just to show you how we do this, first you have an MRI scan and you move your hand, and the part of the brain that controls the hand lights up. You can see it right there. That little glowing area is the part of the brain that controls hand movement. We then use that, not yet guys, sorry, someone's advanced, thank you. We then use that to guide our operation, and this is like DBS surgery for Parkinson's disease. It's a frame, goes onto your head, and the neurosurgeon then will record from the brain, find the area that controls hand movement. Next slide. And then we transplant the cells into some sites along the top of the brain, and the cells go into the brain motor cortex area. They establish there, and they'll release their GDNF and make astrocytes. Next slide. And then this is the very simple 9-hole peg task that we'll ask you to do after you have the transplant. And again, it's an inpatient procedure for a few days in the hospital, and then you're out. And after that is really after the immune suppression, there are no more pills to take, but the pills you will take is more for immune suppression. And we do immune suppression because we don't want the cells to reject. It's a little like a heart transplant. Brain transplants require immune suppression. So we'll give you that temporarily for 1 year, and then the immune suppression will stop, and the cells should be engrafted, doing their work and secreting the GDNF, which is going to hopefully protect your motor neurons. And that's the goal of this trial. Next slide. Where are we now? We have 2 patients already enrolled and underway. We're looking for more patients. If you're interested in participating, we have all the details we can give you. You can go to clinicaltrials.gov. This is the notice. It's trial 05306457. Any further questions you can have, you can contact Pablo Avalos at that address at Cedars-Sinai. So, this is a very interesting trial. It's obviously experimental, and we're trying to understand, can these cells slow progression? The long goal of this work is to eventually combine a spinal cord transplant with upper motor neuron transplant and work towards that as a final stage. But we have to be cautious. We have to go a little slowly, and we have to do the safety studies in order to get to the next stage and show that these cells can be given safely and responsibly to patients, learning whether they slow disease progression and then moving forward. The next slide. So I'd like to thank you all. This is the team. I'd like to point out on the left there, that guy, and we managed to get him out for a dinner, Pat Johnson, who did the spinal cord trial. We don't have Adam Mamalak there, but this is a big team. Next slide. Lots of people involved, particularly at Cedars-Sinai. It's a remarkable hospital in that we can look to all different parts of the hospital for help when we do these trials, from pharmacy to the OR to nursing to anesthesia, pulmonology, and you'll have a very, very professional team looking after you if you come in for this trial. Believe me, there's an enormous amount of work has gone into this. We also have colleagues to make the cells in the regulatory departments and even in my own lab that have really put this all together over the last 10 years. And again, the CERM aspect is critical. The Golden West chapter is critical in helping us recruit patients into these trials. And most of all, I'd like to thank already the 18 patients who participated in the previous trial and the spinal cord trial, because by entering into these trials, we learn about what's happening in ALS, and we're learning about the disease. And it's through these trials that we may end up coming out with novel therapies. So thank you very much. I'll stop there. And I think we can now go back to bring Dr. Lohmann-Herth in, and she and I can answer some questions.
Perfect. Oh my gosh, that was an amazing amount of information from both of you. Thank you. I know our listeners really appreciated it too. We've got some live questions. We've got some questions that people asked beforehand when they registered for this webinar tonight. So I'll try to fold in both And if there is anyone who doesn't get their question answered, we have an email at the end that you can certainly submit that, and we'll get an answer for you later. So, Dr. Svensson, someone's wondering if there are copies of the award winners' posters available to view anywhere, and they just say, "Great work and thank you." Oh, you're on mute.
Yes, I will hand that off to you guys and Jenica as to whether they are available. Maybe they are, and maybe Jenica can let you know. I'm not sure if they are, but I think they probably would be.
Okay, we'll double check.
Thank you.
Another one for you, Dr. Svensson. Someone's asking, can you please share with us some of the new tools and ideas about how ALS can be detected early?
Yeah, that's a fascinating area. And I think, and Dr. Lomenherth can help me here as well because she was at the meeting. I think one of the interesting aspects is one of the most common mutations is C9orf72. So if you have that mutation, you have a high chance of getting ALS. It's very, what we call penetrant. Or if you have SOD1, you're pretty much certain to get ALS at some point. So what a number of groups are doing around the country is looking at patients who carry the mutation and asking, when do they first show symptoms? Because they're carrying the mutation, we know they're going to get ALS. And so there's a big study underway with hundreds of patients being enrolled. So if you carry the mutation and you want to get involved in a study looking at maybe when you first start getting symptoms, that will teach us a lot about how the disease progresses, when it first starts. And I think those clinical trials, and Kathy can help me, have some imaging involved and some other following of these patients. And I'll hand over to Kathy there, but I think that to me is a very exciting area because that might teach us about some of the early symptoms, like in Parkinson's, you get gut problems and smell problems before, 20 years before Parkinson's. And we don't really know enough in ALS yet to know there may be some subtle effects early on that are saying it's going to happen later. Kathy, Dr.
Yeah, well, I just wanted to add that in case people don't know, anyone with ALS can undergo genetic testing for free now. There's a couple of different companies that will do that. You just have to ask your doctor. They can send in the test. And then if you do have a gene, then you can find out if you can be in a particular clinical trial or potentially family that aren't affected yet. So I'd encourage everyone to get tested.
That's great. Thank you both. A follow on sort of from a different person. This is an interesting, they say, how can there not be a genetic basis for non-familial ALS?
Well, I'll go first, and then I'm interested to hear Kathy's thoughts as well. Dr. Lomenherth's thoughts. Sorry, Kathy and I chat all the time, so it's okay. There's this thing called the environment out there, which we don't understand. So I'll very simply say the analogy I like is that genetics loads the gun and the environment pulls the trigger, which means we're all genetically loaded, but the environment plays a role on top of that. And I think things like football players, trauma, some people can probably bang their heads and for the whole lives and not get sick, whereas other people have a few concussions or a small concussion and will get ALS. Now, perhaps they're genetically set up. So your genes are kind of setting you up for a second exposure from the environment. And I think that's one of the jobs of the researchers is to try and figure out how the genetics play with the environment. And that's kind of a complex answer, but I think that's probably what's happening in ALS. It's a combination of being having a genetic risk, but then exposed to something in the environment that triggers it. Kathy?
Yeah, I would just add that I think there's the concept of, multiple genes involved as well. So we know certain genes that do cause ALS in some of these familial cases, but for a non-familial person, maybe they have mutations in 10 different genes, and that particular combination happens to cause them to have the disease or happens to have them be more susceptible to some of these environmental insults, as Clive mentioned.
That's great. Dr. Lomenherth, this one is probably for you regarding the DEI presentation. Does the ALS patient demographic mirror the demographic in our state?
Yes, we know that in the world. We know that ALS is of equal prevalence in all races, and It's a little more prevalent in men than women, so that is a difference, but certainly prevalent and equally prevalent in all races. And I would defer to you, Audra, from the ALS Association standpoint, if you feel like your registrants do reflect this state, or if we still need to do more work to try to encourage patients from different races to join the ALS Association.
I think it does, and I think your presentation is going to be really helpful for us, Dr. Lomenhirth, just, as we continue our outreach into the communities and making sure that we're finding as many people of all races and ethnicities as, are reflected in our counties that we serve. So it's a good point. Another question, how localized to the injection site do the astrocytes, the GDNF producing cells, stay? Will they spread throughout the spinal cord or stay near injection?
That's a great question. And in our animal models, we've shown that, interestingly enough, they do spread. So when you inject the cells, we call them neural progenitors. Progenitor means something before the astrocyte. So we're quite clever. We put in a progenitor, and the progenitors in our animal models will migrate quite a distance in the animal spinal cord, maybe up to 2 or 3 millimeters or even further, which is why we spaced our injection sites 2 millimeters apart, thinking we could cover a large area of the spinal cord in humans. And what we found in the humans is we don't think they migrate quite as far in the human, because whether it's because it's older tissue, the animals are younger, but we do get some migration in the humans as well. And that's the idea, is we put them in and they migrate out. And as soon as they stop, then they start forming an astrocyte and they pump out the GDNF. So we're figuring out we can still get pretty good coverage of almost the whole lumbar cord with these 10 injection sites that we're using, with the amount of migration that we see.
And there's another question, follow-up question. Can you please explain what is immune suppression?
Okay, immune suppression is drugs that we give patients to stop the cells from rejecting. These cells are not your own. They were made from one single sample from a different patient, different human. And so it's a bit like when you have a heart transplant or a kidney transplant. If it's from another patient or another person, your body will reject them. So we give you immune suppression, I should have explained that, to stop the cells from rejecting, and they protect the cells, basically, the immune suppression that you give. Kathy will do a better job than I can, probably. But.
Gotcha. Thanks so much for that. Is the stem cell trial looking at effects on the hand only, as opposed to a broader effect on a person's body?
Yeah, I think one of the powers of the trial that we did in the spinal cord and this one is, normally when you do an ALS trial, that you measure this ALS-FRS score, which is a very broad score of everything and all of your functions as an ALS patient. And that's good and bad. It's good that it covers everything, right? But ALS patients progress at very different speeds. And Kathy will tell you that some patients go very quickly and others take quite a much slower progression. It's hard because you have to have a lot of patients to understand if you have an effect of your drug because of all this variation. Now, when you go into one part of the brain, all we're looking at is hand function. So we can just focus on this because the cells don't migrate away too much. So we know they're only going to affect the hand, because that's the part of the homunculus I mentioned we put them in. So we just follow the hand. And the other strength of this trial, it's kind of unique, is we only put them on one side. So we're only expecting the effect to be on one hand function. So the other hand will go, if it's going at a fast speed, will be a control, if you like, for the hand that's being treated. Now, of course, if we see a massive effect in the first 5 patients, the FDA have said we're allowed to then do both sides. So if this is very significant, and it's an open label trial, this means we don't have blinding. So the subjects know they're getting treated. We can then, what we call crossover, and we'll do transplants on both sides of the cortex. So we're in that phase of, this has never been done before. It's the first time anybody's put cells into the motor cortex directly. And so we'll be watching very carefully to see if we see any effects, any gross effects.
Wow, that's really exciting. Are there statistics how many generations familial ALS can be passed on to? Do we have any information around that?
Sure, I can answer. So typically when you have familial ALS, one of your parents would need to have the disease because it's 50% penetrant, meaning or dominant. So meaning that one of your parents would need to have it, and then 50% of their offspring would have it, and so forth. So it's always like 50% of the family would be at risk for getting ALS. So familial ALS is quite rare, usually just 10% of the total ALS population.
Makes sense. Another gentleman says, thank you for the great presentation. What is it that increases a veteran's risk of developing ALS? Is it an environmental or via the inoculation types received upon entering service?
This is a great question. And we actually have a research grant that we're hoping to answer that question from the Department of Defense in greater detail. But so many different theories have been proposed. High temperatures, being exposed, deployed veterans are more likely to get ALS than non-deployed veterans. Is it excessive exercise? Is it trauma? There's so many theories and not a lot of answers right now. And just to answer that bottom question, yes, the VA has ALS clinics, and the ALS Association is helping to fund some of those clinics. So you can definitely get multidisciplinary care in ALS in some of the VAs in California.
Perfect. Thanks so much for chiming in. Yeah.
I mean, I totally agree. I mean, we don't know. The answer is we really don't know, but the kinds of studies Dr. Lohmann-Hertz just mentioned are the crucial ones that we need to be done to understand more what this relationship is.
Makes sense. Someone submitted a question ahead of time asking about the linkage of long-term statin use as a potential cause of ALS.
Kathy?
I mean, I think statins have been proposed to be a treatment for ALS. They've also been proposed as causing harm. And, from my perspective, your risk of having a heart attack and is important. That if you I guess what I'm saying is, if you are someone who is definitely at risk of having a heart attack, it's probably more important to keep your cholesterol under control with statin use than to stop taking statins.
Gotcha, makes sense. There's a gentleman who's asking about the stem cell trial. He says he's had ALS for 3 years and wonders if he would still be eligible for that trial.
You can always contact our coordinators and ask. It really depends a lot on your forced ventral capacity and other aspects of your ALS. So I would encourage you. I gave the link at the end of the talk, and so please contact our clinic, and they'll give you accurate information on whether you're eligible or not.
That's great, and we can pass that along for anyone who's interested too.
Perfect.
Question, are there cases of remission of ALS? And if so, what have we learned about this?
That's a major topic of study by Dr. Richard Bedlack at Duke. There definitely have been reports of ALS reversals, and I personally have not seen one in all of my years of taking care of ALS patients with ALS, so I think it is quite rare, and I think it is important to recognize that sometimes different disorders can look like ALS, but actually be conditions that are reversible or treatable. So I think I would say it's something that's rare. It's something that can commonly occur in other diseases that look very much like ALS, but there are reports of it happening, and I would love to see a case.
Me too. That's great. Dr. Svensson, how soon do you plan on proceeding with the next 18 patient phase of the stem cell trial?
So we're already enrolling. So for the cortical trial, we're already off. We've done 2 patients, and we'll be up to 16, hopefully within a year. We're trying to enroll at least 1 a month moving forward. For the spinal cord trial, we are going to be soon announcing a continuation of the original trial with a slightly different targeting, as I mentioned, and a slightly earlier stage of disease. And we haven't announced that yet, and we're trying to get our cortical trial off the ground, and it's a huge amount of lift to get that going. And so once that's running smoothly, we'll enroll some more spinal cord patients. Right now, that's the cortical trial is the one that's open and running them.
Gotcha. Okay. And someone else asked, what do baclofen and riluzole do? Do they slow down the neurons? And if so, shouldn't we be trying to speed them up?
So baclofen is a symptomatic treatment, meaning if you have stiffness, then baclofen helps to relax your muscles so that you don't have as much pain and discomfort, and you may move better with treating that baclofen. Riluzole is one of the 3 R drugs that we use to treat ALS: Radicava, Riluzole, and now Relyvrio. And all those drugs are working at slowing down the rate that you're getting worse. So trying to slow down the rate that the nerves are dying from the disease. So we actually do want to slow things down because we want to slow down the rate of cell death. And I'll leave it to Clive if he has anything else to add.
Perfect. No, those are the 3 R's, and we would like to have 10 R's, but we might have next drug may not be R. But
Yeah,
we need more. We need more drugs.
absolutely. Someone else is asking about what, Dr. Lomenhirth, you might be answering this, but what's the success rate on the Radicava clinical trial?
Yeah, so Riluzole slows things down by 10%, Radicava and Relyvrio 35%.
Gotcha. Okay. This one's totally unrelated, but someone's asking, what are your recommendations for ALS patients to deal with the persistence of the pandemic and highly contagious viruses? Many ALS patients use ventilators and are all at high risk for hospitalization and death. How can we minimize the risk?
Vaccination, vaccination, vaccination.
End of answer. That was a great one. I don't see any more questions at this time. We're going to put up a slide in a second to show everybody where they can email other questions they may have. But I really, really want to thank Dr. Svensson, Dr. Lomenhirth for being with us tonight. This was a fabulous presentation. So grateful to both of you, and really to everyone who joined us tonight for your time and your commitment for being a part of this community. Once again, a big thanks to Mitsubishi Tanabe Pharma America for their support. And if you have other questions that weren't answered tonight, please email us at askme@alsagoldenwest.org. We do invite you to save a couple of dates coming soon: our Jim Tracy 5K to defeat ALS and our SoCal Ride, Hike, Walk to defeat ALS are both coming in the next few months. We would love it if you joined us for a beautiful day outdoors at either of these fun, inspiring, and community building events. As you know, philanthropy fuels everything we do, and we're grateful to committed donors who give generously throughout the year. To learn more about how you can support the valuable programs we offer, including like this one tonight, please visit our website at give.alsagoldenwest.org and watch for a short survey on tonight's presentation that you'll receive via email. Thank you so much again, and we'll see you next time.